Welcome to the Geological Society of the Oregon Country. We are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We've been stopping at road cuts, pulling over the car and looking at rocks for, is it 85 years now? We really emphasize that we are a mixture of some people with professional experience that we're very grateful to have here, including today. We have our president, Sheila Alfson. We have Dr. Emily Cahoon. We have Andrew Dunning, a grad student from Portland State. We might even have Scott Burns drop in with us. We have Clark, also a board member, formerly of Dogami. So we have wonderful expertise, but most of us, including myself, are amateurs. And we really try to emphasize that we try to create a space here where people who are amateurs can indulge their curiosity and get to chat with our professionals. And so no question is too basic. You know, what is a rock? What is a mineral? What is a feldspar? All of those we encourage you to either voice later on in the presentation or put them in the chat, and Patty will field them. What do we have coming up? Oops, I'm kind of in the way, aren't I? We always have our lectures monthly. We've been doing that for 85 years, and usually they're at Portland State, but right now they're going to be on Zoom. Our next Friday lecture, November 13th, 7:30 p.m. on Zoom, will be Dr. Anders Carlson talking about monitoring our vanishing glaciers. And his project is pretty interesting. Climate change can kind of be a downer, but being brought into brought into the process of preserving these important natural features. Dr. Carlson is asking us for photos that people might have of what the mountain looked like, what the glacier looked like on your hike 20 years ago. And so we'll put a link up that allows people to share those photos, but he's going to be talking about the glaciers in the Oregon ecosystem. Then the month after that, in December, we're going to have David B. Williams, finally, the author of Stories in Stone. Some of you may know that I've been doing with a number of other members here. We've been doing a downtown geology tour, a downtown building stone geology tour for 10 years now. And we used to do that twice a year. Haven't done it this year, but we are getting Dr. David B. Williams, who wrote Stories in Stone. It is a wonderful book about not only the geology of the stone, but the history of the stone cutting and sort of its history in American history. And so he will be with us in December. We haven't been doing much in the way of field trips, and we have many scheduled for 2021, but through a generous donation from People of Color Outdoors, we were able to do a socially distanced presentation out there. Oxbow Park is a wonderful spot, and that's sort of what it looks like when everyone is spread out 6 feet apart. Finally, again, ask your questions in the chat and we will try to get them to our presenters as quickly as possible. No question is too simple, and especially the one that you're thinking, I'm not sure I should ask this because it's too basic. Please, that's the one you should ask. We are a membership organization. No membership required for attending the lectures or attending this meetup. But if you're interested in supporting the organization, and we do support Portland State geology students with our scholarships, we do support our sister organizations, and also membership is required when we get back to doing our overnight field trips. So if you're interested in those, and we'll maybe, I see that our field trip coordinator is here, so we might talk a little bit more about what we can expect for 2021. Finally, this program is being recorded and it will appear on our website. So just so that you know that. And here is our schedule. Patty's going to lead us through introductions, and then we're going to hand it to Dr. Cahoon to talk about Sunstones. Then Andrew's going to hit us with the geology news, and lots of questions probably will come up in that. And then finally, we'll do a little show and tell and try to end up at close at 1:30 as we normally do. So
thank you everyone for being here and taking the time on a Saturday. Paul and I had spoken, oh, I don't know, time has no meaning to me anymore. So it could have been a couple weeks, maybe it was a couple months ago, about coming in and talking about sunstones. And so the next 20-25 minutes, depending, I think, on questions, I'll be talking to you about Oregon sunstones. And we're not going to go necessarily in what might seem like a logical order, because the question I typically get is, how on earth did you get interested in sunstones? And so the story that I'm going to kind of tell you is through the lens of how this became a project in and of itself. I have submitted now my second NSF grant to hopefully study these. I'll find out in a couple months. So I guess if you don't hear from me in a couple months, don't ask about it. And then I've also recently, I was offered a fellowship with the Gemological Institute of America. So definitely exciting stuff, and yeah, something kind of for anyone. So that being said, get this show on the road. And I'm interested in sunstones because they're classified as a precious gemstone by GIA, the Gemological Institute of America. And I'm starting to get more and more curious about their presence, specifically in flood basalt provinces, which are a type of large igneous province, basically the largest eruptions on Earth that Earth has recorded. This is a picture from, gosh, not this summer, but the summer before. And it was down, there are two areas where, I'll show you a map in a little bit, of where sunstones are found in Oregon. And one mine is sort of to the north, and one mine is about 150 kilometers south. This is in the southern area. I'll be referring to this as Plush. And a number of claims there. This is all on BLM land, Bureau of Land Management. This is one of the southern mines. The gentleman right here owns the mine, and this is probably one of the world's best gemstone faceter of sunstones. His name's Daryl Alexander. He lives in Tucson, and this is Dave Wheatley. He lives actually at this mine year round. So in the winter, gets cold down there. So I'll be going through kind of overview, early motivations, how I even got into this, a little bit of previous work, kind of depending on if there are any questions. And if we get to it, we might not get there. Sort of the proposed research that I'm hoping to do, and the objectives, sort of what I'm hoping to answer. And if you're wondering, what the heck is a sunstone? I will tell you. They are basically plagioclase feldspar. And when you think about feldspar, an analogy I like to use, because there's all of these different names, right? You've heard of maybe potassium feldspar, alkali feldspar, labradorite, andesine. There's all these different kind of things. And I like to think about, if you think of feldspar like a fruit, and then more specifically under feldspar, there's two different kinds, plagioclase and alkali feldspar. Alkali you could think of as is also K-spar. And so under fruit, you could have an apple. But then there are more specific types of apples, right? You can have Macintosh, Granny Smith. And so under plagioclase or alkali feldspar, you can have, again, all of these different subvarieties. So sunstones are a type of plagioclase feldspar, specifically labradorite, which depends on how much calcium to sodium there is. I included a little ternary of our feldspars down here. And I say copper rich or copper enriched, but there's not a ton of copper that would be beneficial for mining purposes necessarily. We're talking 300, 400 parts per million, but you can definitely see it. And because there's copper in them, they are a variety of colors that can be red to pink, yellow, or in the gemstone world, champagne, colorless, and most kind of common, or not common, but a term that is really specific to sunstones, you'll hear schiller, which means that there are copper macro inclusions. They almost look like tiny little pennies that are within the sunstones themselves, and you can see them with your naked eye. You don't necessarily need a hand lens to see them. And it's because of these copper inclusions that you get these beautiful different arrays of colors, which you can see in the upper right. And then in the middle here, these are all, I guess the black pen doesn't work well here, but you can kind of get the idea that these look potentially like there are little pennies shoved in them. I mentioned they were classified by GIA as a precious gemstone, and their hardness ranges from about 6 to 7 on the Mohs scale. And when you have a gemstone, especially if you're going to put it in jewelry, you want something that's relatively hard, right? Because if it's soft, you hit it on a table, you know, there's the chance that it scratches a little bit. So with labradorite, usually closer to a 7, but decently hard. And the thing that I'm most interested in is that they're found exclusively, asterisk, in Oregon, and most commonly referred to as Oregon sunstones. I'll be, toward the end, if we get to it, I'll be sort of explaining that I don't think that they're just found in Oregon. I think it's a function of the unit that they're found in that makes it sort of appear like they're only found in Oregon, but most commonly also referred to as Oregon sunstones. And hopefully I will persuade you that there could be other occurrences. Okay, so just kind of what a sunstone is, but how did I even get interested in these things? Well, they're found in the Columbia River basalt group. And if we, living in Oregon, you're probably well versed in the CRBs, but this is a flood basalt province. It was a vast outpouring of basaltic lava that covered the Pacific Northwest between about 17 and 16 million years ago. We'll call this the main phase of volcanic activity, even though volcanism continued until about 6 million years ago. These things didn't erupt out of, conical centers that you may think of a volcano, but rather elongated fissure or cracks that were scattered all across eastern Washington and Oregon, and they were sourced from the Yellowstone hotspot. So I have the Snake River Plain kind of drawn in here to just give you an idea of the extent of this flood basalt province, and then the source that we think that it came from, the Yellowstone plume. And the Columbia River basalt group can be broken into 4 kind of units or formations on the basis of age, eruptive locations, so where the fissures were located, the mineralogy, but mostly the geochemistry. And that's because basalts are black and they don't often have really identifiable minerals in them. So to distinguish them, you kind of need geochemistry. And that's predominantly how we sort of classify unit to unit. And again, 4, and those are the Grand Ronde basalt, which you may have heard of, the Picture Gorge basalt, the Imnaha basalt, and the Steens basalt. And just kind of focusing in a little bit more, the same text here, but just a little bit more detailed in terms of location. And some of you who know me do know that my dissertation was on the Columbia River basalt group, and more specifically, the Picture Gorge basalt. And that extent is this kind of, maybe a little bit difficult to see, but I'm outlining it in white here. So this kind of polygon was the original extent of the Picture Gorge basalt, a formation of the CRBs. Pretty much thought to be, it's kind of the runt of the family, smallest in spatial extent, volume, and really hadn't had that much work done on it because it's the runt. What more could it tell us? And that was the focus of my dissertation. And kind of out of that, I extended distribution of the Picture Gorge into something kind of like this larger white polygon. And through that, you'll see that that plush area I was referring to earlier, that picture that was on the very first slide, that came from this area in the south. And you can see Steens Mountain down here. So again, just kind of taking you through, okay, what was a sunstone, but where are they, where are they found? And this was kind of the path that got me to become interested in them. So in the same map, I have put 2 little red stars. These are predominantly the 2 places where sunstones are found. And you can see that the southern one is very close to Steens Mountain. So of those 4 subunits that the CRBs can be distinguished sort of into or broken into, this southern location was always thought to be, oh, it's part of the Steens basalt. It's gotta be, Steens is right there, they're basalts, this makes sense. But actually there is not one published or otherwise that, to the best of my knowledge, a geochemical sample from any of those mines that actually correlate them with the Steens basalt. It was just one of those kind of assumptions that was made. And then you'll see this upper star. This is the Sunstone mine to the north. It's about 150 kilometers between them, roughly 80 or so miles. And the map to the right zooms in a little bit on this. So you can see the mine to the north is the Ponderosa mine. And then the mine to the south, I'm going to refer to them as the plush claims because there's a lot of mines down there. The reason is because the mine to the north is on private land, so they own both the land rights and the mineral rights. But to the south, this is all on that Bureau of Land Management land. So there's a lot of claims. And it's because of this distinction in how the land is owned that there's a lot more claims in the south, and there's only one to the north. But early in my dissertation, let's say it was sometime in 2016, I remember my PhD advisor, whom some of you know, Martin Strack, handed me this map and said, hey, there's this northern Sunstone mine. At this point, I don't know what a Sunstone is. And he said, I think you should go check it out. And he was referring to the Ponderosa mine. And the reason he was doing this is because as I said, my dissertation research was going to be focused on the Picture Gorge basalt. So he thought, well, if we're thinking about extent of the Picture Gorge, and sunstones have always been thought to be steens, what about this northern one? The location is roughly too far north to be steens, and if it has sunstones, it's kind of that idea, but you should go check it out, see if it could be Picture Gorge, because as you can see, it kind of sits in between the extent, like the southern extent of the Picture Gorge and the northern extent down here is sort of the Steens basalt. So the idea was go check it out, grab a sample, right? See what it looks like, throw it with the rest of your samples when you do some geochemistry in the fall, see what happens. I thought, fair enough, I'll go do that. But I'll point out that even though there's a coordinate here, there's no directions really, like there's no close road. So it actually took me, embarrassingly enough, a bit longer to find this mine than I care to admit. But so back in the summer of 2016, I went out there alone and just tried to find this mine. It was actually kind of hard to find. And I got there, and this is that same map, except now I'm just highlighting just that northern mine. This is the Ponderosa mine. This is a picture of camp. There is one building that is there year round, and the rest people kind of come in trailers. And then you can see a number of these buckets in here, 5-gallon buckets, all full of sunstones. And they just have them sometimes just sitting in buckets. They sort them as they're coming out by color. So sometimes they'll have a bucket of clears or colorless, a bucket of shillers, a bucket of reds. If they're too fractured, sometimes they're not kept in kind of a special bucket. But after that first summer, I did some geochemistry, and what you see on this upper right-hand diagram, we call these spider diagrams. The ins and outs of these aren't super important, but I just want to highlight that each one of those CRB units is in a different color. So I said the Grand Ronde in green, Picture Gorge in gray, Imnaha in yellow, and then those two Steens are just, the Steens basalt are just, I have split here. And the only thing to kind of take away from this is that after that first summer, when I got that sample back, I realized, oh my gosh, of all the units, it definitely doesn't look like Steens basalt. It looks more like Picture Gorge. And that's where this whole thing kind of stemmed from. And it was just a function of thinking about what is the extent of two of these formations within the CRBs. So pretty cool. I was really excited about this, but not because of sunstones. It was because, hey, I know where we're starting to realize that the Picture Gorge basalt likely extends further south than we thought it was. And that was kind of the early motivation and excitement. It wasn't in the context of studying sunstones. And after that, I thought, heck, what about the other mines? And so a couple summers later, because this is over the extent of my PhD, so this is a couple, 2-3 years later, I went down to the southern mines got 2 different samples from 2 different claims down in the Plush area that were 15 miles apart, so not necessarily right next to each other. And what I realized was for the 2 different mines that I went to, they were both, again, looked like they were picture gorge basalt. And so with both of these, you can see my samples that I was taking were in black, and for the most part, they look very similar to the gray lines. You may notice between both of these that the one deviation for the samples in black are here, right? There's these sort of peaks. That is because if you are a chemistry nerd at all, this correlates with the element strontium. And strontium sometimes substitutes into plagioclase in the calcium site. And it's because of this, these samples have more strontium because they have so much plagioclase feldspar in them. Okay, so that was kind of leading up to it. And so we kind of know what sunstones are, but I guess in a little more detail, they were originally identified as, because sometimes sunstones can have hematite in them or other kind of more metal associated inclusions, but copper was first identified 100 years ago now. And then in 1985, it became the state gem of Oregon. First kind of study was done, I think actually Clark shared it in the chat a little while back, was by Stewart and some others in 1966, and then further examined by 2 other people, including George Rossman, who is now at, he's at Caltech. He's technically a physicist, but he did a study on kind of the oxidation state of the copper. And at that northern mine, another study was done in the early 90s, basically confirming, yep, this is also copper, and looking a little bit at the oxidation state of the copper and what the differences were between some of the colors. More recently, and not to sound negative, I'm just a little bit becoming more and more skeptical of this next study, but there has been a type of pyroxene mineral identified in sunstones, which is thought to give it some of the green coloration. And this is an interesting variety of pyroxene because it is typically found at very, very, very high temperatures. So actually observing it at the surface is a little bit tricky to do because it should revert to a more stable form called clinoenstatite. So I've talked actually a bit with George Rossman about this, but I'm each day a little more skeptical potentially that there is protoenstatite in sunstones, but they have been identified in some of these green areas. And this was a study a couple of years ago. And overall, because of their color, they're beautiful. The price can range from about $10 to $1,000 per carat once they're faceted. And I think the kind of fun is that they are ethically mined, they're locally sourced, and a lot of people here know how much us Oregonians love our local goods. And they're becoming more and more popular across both gem and jewelry markets because of this sort of, they're not heat treated. Each one is very, very different because of those inclusions of copper. And I think more and more as sort of the younger generation is moving away from more traditional gemstones like diamonds and sapphires and rubies, they are picking up a little bit more interest. I'm going to kind of skip over the nitty gritty here, but kind of the work that had previously been done on sunstones was motivated from actually something kind of bad that happened 20 years ago now. And it's when a bunch of sunstones started flooding the market. And anyone that owned a mine or was selling sunstone jewelry was like, where are these additional sunstones coming from? And it was from China. It was a little bit hard because the people selling them often don't also own the mine. So it got a little confusing because they were coming from China, from Inner Mongolia, Tibet, the Congo. And after a couple months, it became clear that there's more of these but we haven't seen any of them in the actual basalt. We haven't seen any pictures of mines. We're just seeing them on the market. And that skepticism sort of continued to grow. Eventually, it was determined that these sunstones coming from other places likely weren't natural, but rather clear feldspar that was then heat treated with copper to promote the copper going into the plagioclase and then eventually looking like a sunstone. So many of these did look red, but they were basically man-made, not the crystal, but the coloration. And this wasn't a new process. People do this with sapphires all the time. So most of the time, actually, when you see a blue sapphire, it's probably been heat treated and it sort of enhances the coloration. And this basically the same process was happening, except instead of just heating it, they were heating it with copper. And you know, keeping track of the temperature and the pressure and sort of how much oxygen was in the furnace and producing apparently sunstones. This eventually came to light and has now, if you can't demonstrate really clear evidence that a sunstone is from a new locality, it is not met with excitement. So at this point, the idea is that there are no other sunstone locations. People at GIA, George Rossman, there's a lot of controversy over, do these exist? The consensus is sort of, there is probably a few other places, but they are so minor in volume that somebody probably saw it and thought, hey, it's here, but let's take a bunch of clear ones and heat it with copper, and then it'll look like this is a larger deposit than it really is, but still the source of some arguments. And then kind of out of this, 10 years after this started happening, some studies were done where they basically took a clear sunstone or a clear feldspar and heated it with copper to see what the color would do. And you can see from, these were the results. Actually, this first guy, John Emmett, actually lives just over the river in Washington. And I met with him last year, and he showed me some of these and explained what they did. And basically, the problem that they ran into is that if sunstones indeed were being heated here, like we can see we can see these coming out in Oregon, like these are natural, but trying to think about how the copper gets into the crystal in the first place, they did some heating experiments. And the first thing was to prove that likely the sunstones from these other places were in fact being heat treated. But the other thing that they noticed about Oregon is that if the copper was going into the crystal after the crystal formed, the profile of copper and coloration in the crystal doesn't make sense. And this becomes important when we think about how copper is getting into the crystal in the first place. And I'll talk about that in a few slides, but the kind of point of this is a bunch of sunstones came into the market 20 years ago. Turns out they weren't, even though the crystal was real, like crystal was natural, the coloration was not. Downside, it really hurt the market for a little bit, but it brought, some will say any press is good press. And so sunstones are a much more widely known gemstone because of this whole controversy. If you've seen the movie Gold, it has Matthew McConaughey in it. I think it came out a couple years ago. I don't want to give away this movie, but if you've seen it, you'll make the connection to what I'm about to say. Eventually, some people through this whole controversy from GIA and also the Gemological Society of Great Britain went to some of these so-called locations of sunstones in Tibet. And what they started noticing is the people that were taking them to these different mines would take them and then say, hey, you should dig right here. And they would do it. And sure enough, find a sunstone. But they were told to dig right here. It took a bit, but it was understood that the ground had been salted which means that somebody had basically placed sunstones there for them to find. There was a lot of work done on the differences, but this has had a bit of a controversial past in terms of when someone comes out to GIA or just to even like the American Gem and Trade Association and says, hey, we found more sunstones. It's not met with a lot of excitement because this has just had a rough couple of years. I should mention that another way that they determined that sunstones weren't, these sunstones weren't natural is they weren't dating them, but they were dating some radiogenic byproducts of what should be in the crystal. And if you're at all familiar with any sort of radiometric dating technique, you have a parent isotope and a daughter isotope. The parent decays to the daughter, and over time, more and more of that daughter isotope collects. Well, if you heat these crystals, it can allow the crystal structure to expand enough, and it resets that radiometric clock. And all of the sunstones that were from these additional places, they were noticing had very little radiogenic argon. And so part of the conclusion was, yeah, these have been heated up recently, and that's why there's no daughter isotope. Does anyone have any questions kind of about any of these aspects? I don't want to
at our
talk too
half-hour
fast.
point, so if you want to.
Oh, yeah, all right. Perfect, okay. So in essence, a lot of issues, but more recently, there has been a new site in Ethiopia, and there have been 2 studies done on this, and it is looking more and more like its potential. And GIA came out with an article just a couple months ago. If you Google GIA Sunstones Ethiopia, especially in Google Scholar, you'll see this this paper come up. And basically, this is what part of my research is going hopefully to be on, is understanding the differences between Oregon sunstones and these new sunstones that are coming out of Ethiopia. Even though this is met definitely with some skepticism, there has been enough geochemical studies on these new Ethiopian sunstones that it is becoming clear that they cluster in a lot of geochemical space with Oregon. And what I'm also hoping to discover is whether we know the crystals are magmatic, but did the copper go into the crystal when the crystal was forming, or later, closer to the surface from some hydrothermal processes that mobilized copper? And kind of this is the more of like the nitty gritty of the study itself. We'll hopefully do some dating. I did have a student actually work on the copper concentrations in the basalt to see, could the copper actually be getting sucked out of the basalt and put into the plagioclase? The answer is no. We don't think that's what's going on. And the last thing I just kind of want to show you is thinking about the purposes of this. This has applications, not just to, okay, cool, this is a unique thing, but it also has correlations to understanding continental flood basalts, because that other location in Ethiopia is hosted in the second youngest flood basalt province. And what I'm proposing is that maybe they aren't this, while yes, they are, I like to think that they are unique to Oregon, we have the world's youngest flood basalt province. And if the 2 now kind of only confirmed locations of sunstones are in the world's 2 youngest flood basalts, it's feasible that it's a function of, preservation potential and just how old the hosting flood basalts are, and that sunstones are actually recording a process that is unique to flood basalt. Hopefully, I'll find out in a couple months if I'll be able to explore this in any more depth, but it's exciting because it's gemstones. You're kind of supporting in some way the local, kind of geotourism, and on a broad scale, applications to petrology and large igneous provinces. And that's what I got. I'll stop
Thank you. I see some applause in the background. I'm going to embarrass myself because I was a little distracted at the beginning, but I'm still puzzled how you get feldspar crystals coming out of basalts. Did you explain that?
I didn't. So in terms of how they're coming out or how they're forming.
I guess that's sort of how they're forming, and then, yeah, I guess maybe how they're coming
So
out.
the idea is I don't have a cross section of a magma chamber necessarily, but in a magma chamber, when plagioclase is forming, it is not denser than the liquid. So when they crystallize, they can float to the top of the magma chamber. And if you have a new injection of magma, it is feasible that you could remobilize almost this like mush of plagioclase and bring it to the surface. That is the working idea. The one minor problem I have with that is that you never see almost like enclaves of a whole bunch of plagioclase crystals like stuck together. They're always discrete crystals.
Okay, so it's more like a porphyry in a sense. It's crystals that are already formed in the magma. It's not something that happened later in the vugs or something, that not like agates or something that.
Absolutely, yeah, they are primary. And if you are an oxygen isotope person, their oxygen isotope values, I've only done a handful, but they reflect more of a magmatic origin than a hydrothermal origin.
Interesting.
And the other thing is thinking about their, like, if they were surficial, like if this was something happening later, really weird that you would get the most perfect situations kind of happening 80 miles apart. If they're not sourced from the same place.
That makes sense.
And so actually Nolan here is going to be trying to learn more about the fact, are there other instances in between these two locations?
Okay. It looks like we have some questions in the chat. Patty, you want to? And you're not muted, but we're not hearing your mic. Still not hearing it. Oh, now you're muted.
So yeah, I can see some of these in here.
We won't have Patty's voice, but if you want to read them out, Emily.
Yeah. So Sheila was saying that the Rice Museum has samples of artificially colored stones in one of their rooms. And I should say I've been, the new curator there is actually a PSU grad. And so I've been over there a handful of times. I don't know about the poisonous ones or if they're like how they're artificially colored. I'm not familiar with those.
From Sheila's remark, it's not clear to me that they're given to children to poison them, or whether they shouldn't be given to children. I'm not.
Yeah, they're often given to children just because they're pretty, because they are unusual color. But the way that my understanding is, the way that they're heat treated, they are poisonous, and kids tend to put things in their mouth, and it's not the best idea to do.
Good to know.
Yeah,
I didn't know that.
Go ahead and look at it in the Rice Museum in that southwest corner of the house. I can't.
Yeah, I was there last week.
And I'd like to go meet the new curator too. So I've been working with all the curators there.
Yeah, she's wonderful.
Yeah, good. That's
okay.
good.
So don't give sunstones to children. Don't put unknown gems in your mouth.
Sunstones necessarily. They're not all sunstones, but they just are really unusually colored rocks. And you tend, if they were natural, you'd go, wow, that's a really great specimen, but they're not natural. And, and I'm not sure exactly what they do I know they heat treat them, but they also, that was new to me, that they inject things in and then heat treat it. I don't know.
They do a lot of things to bring out color.
Yeah.
And we have a question from Carol Hassenberg. Go ahead.
Yeah, and she's asking, are Ethiopian flood basalts associated with rift volcanism, and what is the age? Great question. The Ethiopian flood basalts are approximately 30 million years old. You do sit in sort of this, it is very close to the East African Rift, and so the age is, yeah, about 30 million. The big question is that even though I know that the location of the Ethiopian Sunstone mine is within the spatial footprint of the Ethiopian Yemen flood basalt, there is no, to the best of my knowledge, there's no age from that mine. I have been invited to visit from the owner, and the first thing actually that I want to do is date it to just confirm that indeed they are associated with Ethiopian flood basalt. And I think rifting does play a role, but it's primarily plume driven.
Thank you.
But those kind of can be one and the same sometimes.
I just wanted to also, I was over at the Rice Museum recently, and Angela Pillar is the new curator. And
yes,
they also have
her
some
name.
really cool sunstones in their collection, because Leslie Moklock showed us one that was carved. It was really spectacular. So I just wanted to mention that to everyone.
Yeah, and that the faceter that I mentioned at the very beginning, you may see his name under some of the, if you went to that area where they have all the cut sunstones, his name's Daryl. And the Rice Museum offers also classes on faceting, and I signed up for January, so stay tuned. We'll see if I can actually cut a sunstone. And then I see, how do you know if you're getting a real sunstone with all the fakes? Could a jeweler be duped? And 100%, 100% somebody could be duped. I would love if an outcome of this research is a cheaper way to distinguish between the real ones and the fake ones. I do think, depending on the jeweler, if you have someone who is very well versed in sunstones, they may be able to tell. But one thing is that with real sunstones, often you see the largest concentration of color in the center, which is odd because if you think about diffusion, you would get, if the copper was coming into the crystal after it formed, you may expect the highest concentration of color around the edges rather than the center. And that is they can't duplicate that. So I think if you had a crystal that was a deep concentration of color in the center and then was clear on the rim, you could feel pretty good that that was natural. But if you see one that is more, not uniform, but you don't see any differences in terms of color from the center to the exterior, not that it's fake, but I would be a little bit more hesitant.
Good to know. Well, looking forward to more research and actually the chance to see some of these in person, because I think I've seen them at the the Fossil Cartel and other rock shops, but I've never really paid very close attention to them. So thank you, Emily. Hope you please feel you have an open door. Come back anytime. We'd love to have you on our panel of experts for our show and tell. And if you can stick around, we might have some more questions for you. Oh wait, we got one more question.
Thank you so much.
From Jim. Jim asks, since stones come from flood basalt, does distance from actual fissure matter? Where sunstone?
That is a great question. Unfortunately, we only see sometimes evidence of fissures now as dikes or potentially spatter. It's a good question. I want to say, because there's such a high, almost like crystal cargo in these lavas, because the crystals are so big, they have a really high viscosity. So it sort of also more makes you think like the mine to the north and the mine to the south, it is very unlikely that they flowed between the two, because they would have had such a high viscosity with so many crystals and oftentimes being really coarse. So those would have to be sourced from two different fissures. But that being said, doubt they would be able to travel that far from the fissure themselves. So I think you could say something that they would have to be pretty close to a fissure just because they can't travel that far.
Okay. Interesting.
Thank
Well,
you.
thank you. We're at our 1 o'clock point, and it's time for the geology news. And Andrew, it looks like we're going to run over, as we sometimes do for our show and tell, but I don't want you to rush. I want people to feel like, ask questions of Andrew or other questions that come up for any of our other panelists. And we'll let you share your screen when you're ready, Andrew.
Feel free to ask your questions or interrupt me. I don't care which.
Perfect.
And I apologize if you can hear the construction site across the street decided to, oh, you have to co-host me, Paul. The construction site decided to turn on their concrete grinder for the first time on a Saturday. So it might get a little rumbly.
All right. You are a co-host.
There we go. How's that?
Perfect.
Start this over. There we go. All right. Welcome to the Geology News for October of 2020. I'm Andrew Denning, graduate student at Portland State University, just starting my master's degree. And I'm going to bring you the news of the month. I like to start with earthquakes because I'm an earthquakes enthusiast. I study them under Ashley Strag, who gave a talk a couple of weeks ago, I believe, for GSOC. The largest event in this last month was a magnitude 7.6 off the Aleutian Islands off of Alaska, which is a fairly considerable earthquake. It's very close to the epicenter of a 7.8 earthquake from July 22nd, which was also a strike slip earthquake. So this is a lateral movement, a strike slip. It doesn't have too much vertical slip on it. And the reasons for why there's a strike slip fault in the middle of a subduction zone is confusing, and it seems like the seismologists are kind of shrugging their shoulders at it, saying, we don't know why this is happening here. It's obviously a very poorly monitored area because it's all under thousands of feet of ocean water. This subduction zone here is the same one that ruptured in the Good Friday earthquake 1964, the 9.0 second largest earthquake ever recorded, 9.2, excuse me. So we have a compressive force here, which usually doesn't lend itself well to these strike slip sort of horizontal earthquakes, but nevertheless, it happened. There's no tsunami, no damage, no fatalities reported because it's pretty remote. There's a handful of other magnitude 6 earthquakes around the Pacific Rim. I was not able to find any significant reports of damage, so that's good. And for our West Coast Northwest earthquakes, there was a magnitude 2.5 near Longview. So that's a very small earthquake, really consistent with background seismicity we see here in the Pacific Northwest. I'm going to move on to volcanoes next. There are currently 15 volcanoes with eruptions or ongoing activity, which includes steaming, fumaroles, and lava lakes at a number of volcanoes. There have been 2 new eruptions in the last week, both on the Kamchatka Peninsula, Karinsky and Kluchevsky, which are in Russia. And there's a small ongoing earthquake swarm on the flanks of Kilauea volcano. And I didn't put it in this volcano slideshow, but the crater lake that is formed at the summit of Kilauea has reached 150 feet deep. It formed after the 2018 eruption when the summit of the volcano collapsed into a big caldera, and that has been filling with water ever since. I'm going to start with the sad news first, and that is the climate change, which will continue to affect our planet for decades to come. And we have had the hottest September on record, and 2020 is therefore on track to be the warmest year recorded. This September was 0.8 degrees Celsius on average globally, higher than the September of 2016, which was the previous warmest September recorded. All of the last 5 years of the hottest on record, and the September-October Arctic ice minimum is at its record lowest level. There's record melting in Greenland and permafrost in Siberia. Antarctic glaciers are melting rapidly. And some large glaciers in Greenland and the Antarctic are approaching a sort of point of no return in their retreat. So that's It's not what we like to hear, but nevertheless, it is the news. So I'm going to go to the fun stuff now. And this was my favorite thing from the last month that I saw. This happened actually just a few days after the last geology news segment. Was White Sands National Park announced the discovery of the longest fossilized footprints from humans found in the world. There are some other famous fossil human footprint tracks found in Africa, and those are much older, but this is the longest series. They did not say exactly how long it was, except that it was over a kilometer. So we have these sets of footprints from an adult and a child that extend for over a kilometer. There were little seeds they found in these footprints. This is in ancient lake bed mud in the White Sands National Monument Valley. Lake Otero was the ancient lake bed. And these seed grains and these pollen grains found in these footprints were able to be carbon dated to about 10,000 years ago. So 10,000 years ago, a woman and a child walked across a lake bed in New Mexico. Very cool. I love this kind of stuff. The Mars Reconnaissance Orbiter, the Mars Reconnaissance Orbiter has discovered some compressed paleodunes. So these are literally fossil sand dunes that are no longer active. They're not blowing around the surface of Mars anymore. They're solid rock. They're sandstone now. And they're probably about 1 billion years old, which reflects climate stability. So we know Mars has been dusty and dry and sand dune favorable for at least 1 billion years, which is an awfully long time. A 1.2 billion year old meteorite impact was found in Scotland, the oldest yet discovered. It deformed some soft mud sediments that would have been marine in origin. The interesting thing about this is that this old meteorite impact predates the existence of life on the planet. So that's neat to have such an old feature preserved. A new dinosaur, we got a new dinosaur.
Andrew, I'm going to interrupt you.
Oh yes, please do.
Because sand dunes compressed into rock is something that I didn't know about. Can you explain that process a little more? Do we have something similar like that on Earth?
Yeah, we have on Earth we have old sand dunes. I mean, so they probably haven't been compressed because they didn't get buried, but they are lithified. They have solidified by some process or another. And I don't know if we have a good analog for that on Earth. I'm not familiar enough with sand dune processes, but
Navajo Formation. The Navajo Formation is a good one.
That's what I was going to say. The Navajo Formation in sort of Utah, New Mexico. It covers an enormous area. Is the most famous sort of sand dune, ancient fossilized lithified sand dunes that dates back to the Jurassic, I believe. Blankets much of the Western U.S. But those got buried. Those got buried under many kilometers of rock before they got compressed into sandstone. So we got a new dinosaur in the last month that got published, the Oxoco of Varsan from 68 million years ago. So that is the latest end of the Cretaceous was when this dinosaur died and became fossilized. That is just 2 million years before the extinction of the dinosaurs. And it was discovered in Mongolia. It's toothless, it's beaked, feathered, and is avian in anatomy. And interestingly, as most birds or bird types have 3 fingers, this one has 2 fingers. Some ruins in Israel, some ancient buildings have been used to estimate earthquakes near the Sea of Galilee. This was a new paper that got published early this month, and they were studying some of these old buildings. These are Roman Byzantine buildings. The ancient town was called Tiberium. And as you can see in this wall here, it's slightly deformed here. That's not what you want to see in the wall of your stone building. But this ground deformation here allows us to estimate the size of this earthquake using scaling relationships and a few other parameters of earthquakes that are very well understood and pretty universal. And they were able to estimate the magnitude of this earthquake to between magnitude 6.9 and 7.6. That's a considerably sized earthquake. It happened about 749 AD.
What are those blocks of stone? Do you know, or did they say?
It didn't say in the article I read. I'm not familiar with what Romans were using to build their city structures 2,000 years ago. But the interesting thing that this allows us to understand is, so we don't have records of large earthquakes really in the last 1,000 years, and not at all since modern seismometers have been around for the last 100 years. So if an earthquake happens somewhere, it will certainly happen again. And an earthquake of this magnitude in Israel would be extremely damaging. So this gives us sort of an idea on the past seismicity of the area and what we can look for in the future and prepare for. Here's my note on Kilauea River Lake. A new paper modeling sediment impacts on subduction zone earthquakes. I couldn't find a good figure in their paper that really illustrated their point, so I didn't use it, even though it's kind of a difficult concept. So when you have a subduction zone, you got an old oceanic plate starts to go down under a continental plate. This process is called subduction. That's what happens offshore of Oregon, Japan, the Philippines, South America. There's a lot of these subduction zones around the world. And subduction zones are responsible for the largest earthquakes that occur on Earth. The magnitude 9.3 Chile earthquake, the Good Friday earthquake, Japan 2011, 2004 Sumatra. These are all the largest earthquakes recorded. They're all in subduction zones. And we're trying to understand when, why, and how these earthquakes happen, where, when, and where they do. And this new modeling procedure that they did sought to understand the impact of sediment and subduction angle on the recurrence and magnitude of these subduction zone earthquakes. And they found that shallow subduction combined with a thick pile of sediment produces the largest slip. When an earthquake ruptures, the ground rebounds a certain amount. And that's the actual slip of the earthquake determines how much shaking, the ground velocities, and the magnitude of the earthquake are all related to that. So compared to the previous model where earthquake size and slip amount are determined by the age and therefore temperature of subducting oceanic plates. But this model is emphasizing that sediment packages and the amount of oceanic debris sitting on top of subduction zones seems to influence that quite a lot.
So this is a computer model, I assume.
Yes, correct.
Where would you find shallow subduction angle and then a large sediment layer? I mean, what are there actual earthquakes that we know that have those characteristics that can be correlated to the model?
See, I'm not sure. I didn't read through the whole paper because it's quite dense. I read the abstract and I glimpsed through the conclusions.
Mm-hmm.
Nothing stuck out to me as a current example of this, but just understanding the relationship is very important. So the Japan earthquake, 2011, a very thick sediment package called an accretionary wedge. That's probably a pretty steep subduction angle though, because the subducting Pacific plate is very old, like 250 million years old off the coast of Japan. I might be off by a few tens there. But it's very old, it's very cold. So when it hits the Japanese crust, it's going to drop down pretty steeply.
Uh-huh.
You have sort of a shallow subduction angle here in the Northwest, but not a very thick sediment package. So really it raises questions as well as clarifies some others.
Interesting, thank you.
Something else that was very exciting for me, a new paper was published on the uplift of the Sierra Nevadas. And if you've ever been to Owens Valley or the Sierra Nevada mountains in California, then the eastern face especially, you have in some places 10,000 feet of vertical relief. And understanding how fast that went up is very important for understanding current and past tectonics in the area. And so this new model and the new studies they did showed it to be far faster, about twice as fast as previous studies found, that the entirety of the Sierra Nevada uplifted in about 1.4 million years, which is really fast.
That's fast.
Yeah, when you're uplifting something, I mean, so these rocks, these granites would have formed between 8 and 20 kilometers down. So they would have had to come up 25 or 30 kilometers in.
So Andrew, can you explain first how they formed? Because some of us know that, yeah. But then how it is that you have granite mountains jumping up out of the earth.
Yeah, so these granites, these are the ancient roots of volcanoes. Back in the olden days, there was a plate called the Farallon Plate, which was subducting under North America at the time, and the Juan de Fuca Plate, which we have offshore now, is a remnant of that. And as it's subducted, it causes melting in the mantle and in the lower crust, and that causes volcanoes. And this magma pools in the crust and creates these huge magma chambers, which slowly crystallize over time. And you get these, what's called a batholith, which is a fantastic word of all these magma chambers all kind of stuck together, intertwined and interlinked.
So is it fair to say that we have something like the Sierra Nevadas forming under the modern Cascades?
Yes, at depth there's a significant batholith that stretches from really from about the northern end of the Sierra Nevada clear up into Canada. It's in a few 100 million years, it's going to be very scenic.
So why do they
The
pop
bottom
up?
line is these had to uplift very quickly.
Yeah,
and
why do
very
they pop
deeply.
up?
Yeah, but and their model showed that because of the rate they got uplifted, it was causing melting inside some of these rocks, and that's called adiabatic melting, where just the release of pressure inside the rock causes melting, and that could be fueling volcanics in the area, which we see in COSO. In Kennedy Meadows, there's some volcanics. There's a lot of young volcanics in there in the Sierra Nevada. So it's very interesting. It's very complex. And I look forward to reading the whole paper when I have time.
So there's some adiabatic metamorphism in the Sierras?
Melting for sure. I don't know about metamorphism.
Okay, all right. Interesting. Thank you.
Can I ask a question?
Yes, Carol.
Is it the geometry of the plate boundary there that is putting pressure on those mountains to do this, accomplish this uplift? Is that what they think?
Yes, I mean that is why they got uplifted. So the subduction zone off of California really died about. I'm trying to remember. I talked about this in my Death Valley presentation, but
Yeah,
subduction zone,
I think it was what,
subduction zone-
20 million?
Yes.
Yeah, it died about 20 million years ago, and that gives us the onset of the Sierra, the San Andreas Fault, and the extremely complex relations that are going on down there. We've got crustal blocks of different ages and different strengths all interacting and moving together. The Sierras really act as one single block generally, that are kind of being pushed north by the Southern California blocks and being kind of twisted around because the San Andreas is torquing the bottom end. It's really complex, and it's very much an active field of research trying to understand how it all links together. And so this eastern face, there's some faults on the western side as well. This eastern face is really steep, and the Sierra Nevada front does produce large earthquakes. One of them happened in 1872. The Lone Pine earthquake was, I believe, an 8.0, which is the same size we see on the San Andreas Fault. Those are very large earthquakes. And I believe that had 18 meters of slip at its greatest point. So large earthquakes happen there, and when the Sierra Nevadas move, they move a lot.
Mhm.
So the particular strains that happen in the Sierra block are favorable to very rapid uplift. Death Valley, just 70 miles away or so, dropped down in about 1 million years.
And by the way,
That's
we
also
have
very
an
fast.
excellent lecture on Death Valley on our website from grad student Andrew Dunning. You can find on the gsoc.org website.
To finish up here, actually, I think of one more after this. Yep. So we landed this was just a few days ago. When was that? Tuesday. Our space probe, NASA space probe OSIRIS-REx, landed on an asteroid in the asteroid belt. It launched a few years ago, and it made it to the asteroid just a few days ago because space is very large. And the low gravity in the asteroid really made a touchdown difficult because you just sort of bounce off because it doesn't have enough gravity of its own to hold the spacecraft there. Let's see if the video will play. There you go. Kaboom. It bounced off, and in this little cup at the end of this arm here, hopefully it collected some asteroid fragments which will return to Earth around 2023. And this will give us great insight to the formation of planets, asteroids, and the origins of the solar system. A very cool exogeology is going on at the same time as cool geology here on Earth.
Any idea what we're hoping to find from that pile of rock?
I don't know enough about asteroids or meteorites to answer that question. I personally, I would expect it to be similar to other meteorites that we have on Earth that give us, hopefully they give us insights to the deepest insides of the Earth even, and how rocks evolve over time with heat and what happens when they sit around for a while.
Mm-hmm.
there's a lot of implications for meteorite science that can in fact
Excellent.
impact on Earth. What did the Earth look like 4 billion years ago, for example? Nope. Okay, so excuse the low resolution thumbnail. I have the full map pulled up in another window because it's enormous. A new geologic map of the Portland area was published by the USGS. They've been working on this for about 5 years. So this is a huge project combining mapping from dozens of different scientists to half a dozen government agencies. It's a huge, huge scale map. If you were to print it out to scale, it would be about 13 feet by 13 feet. So it's a big map. And it goes from the Coast Range Timber, the town of Timber's about here, clear out to Troutdale in the east, and it goes from Amboy in the north to Silverton in the south. So it covers a very large area, and this gives us a great understanding that even city officials can use in planning for emergencies. You can see all these faults are mapped here. I'll pull up the full-size one, another window actually. It's still loaded.
Maybe we can drop the link into the chat.
Yes, I will do that as well.
And in fact, I had it printed out. I went to UPS, not the full 13-foot map. I had it printed out in poster size. And so maybe after we finish and we turn off the record, I can do an unboxing because it's still wrapped up.
I think that's a good idea. Let's see if I can pull it up here. It's an 85 megabyte file. How's that coming through?
Yeah.
That's beautiful.
Yeah, it's very exciting. And it's at a very, very large scale. It's got, so these, I don't know if you can see in these contours here, they're very light gray. These are depths of sediment in the Portland Basin. It's actually deepest right around Vancouver Lake here. Really, really fine, good scale mapping of the Columbia River basalt flows in the Portland Hills, and of the volcanics and the sedimentary rocks in the Coast Range.
Beautiful.
Yeah, down here in the Boring Volcanic Field, all the different cinder cones and volcanoes down there. All of these rocks down here in the Newberg area. I can't remember the structural name for that area. But very exciting, or I'll copy the link here, and you can check it out on your own time.
And that's also available in ArcGIS format for people who have access either to ArcGIS or QGIS. One of the things we would love to get from a map like that, and I don't know if anyone has the skills to do this, is to get Google KMLs that you can put into Google Maps that you can have on your phone or mobile device. And then they have to be sectioned off, I think, at this point, because you can't put the whole map on your phone. But that means that you can, when you're out and about, you can look and see what geological unit you're in. And we found that to be very useful in the past.
It's geo-referenced as well. So if you're familiar with Avenza or any similar applications, you could download it onto there. It would be huge though, and it would probably be very taxing on your device.
So what, you'd have to break it up into sections?
Maybe.
Okay.
It would probably work on its own. It might be a little slow.
If Andrew, if anyone or anyone else, if we could work on that for some of our projects, it would be nice to have that out in the field when we go back out in the field. And
it's not a bad idea. I actually have 100 megabyte map of the Clarno area, the John Day fossil beds that I put on my phone that worked.
Okay.
It's a little slow though.
Well, let's talk more about that. Okay. Thank you.
And that concludes the geology news for this month. Thank you to Scott and Patty and Paul for all sending me way more stuff than I could possibly use.
That's wonderful. Now I did see, I look at Google News and I look at the science headlines. I did see that we have these potential catastrophic earthquakes or some alarming headline about potential for crustal earthquakes in the Portland area. And Andrew, did you see any of those headlines and know what that's about?
They, for some reason, the publisher of the paper declined to do a press release about it. But some other local sources and IRIS and SSA and some other sort of publishers and earthquake news outlets did publish about it. I haven't seen any local journals talk about it yet.
Uh-huh.
But it's,
So
it's
you're talking about Dr. Stride,
Yes.
Ashley, who just gave our lecture. Her paper came out, and who else is on that paper? Ray Wells.
Alison Horst was the grad student friend of mine and
Oh, okay.
Emily's, former grad student at PSU. She graduated about a year and a half ago, but the paper just got published. So that shows how much rigor and time the peer review process can take on some of these papers. The gist of it is that we're not paying close enough attention to the numerous crustal faults in this part of Oregon, specifically these strike-slip faults, and even just this one study among maybe 2 or 3 others for the Gales Creek fault, which stretches from Hag Lake up through kind of close to Forest Grove. I can't remember exactly where the southern end is. But that's now one of the better understood faults in the north, in Oregon at least.
It's just an interesting example of science journalism that the headline was, terrible earthquakes in the Northwest, and then the subhead was, but they only happen every 4,000 years.
Yes.
Which is more or less what Ashley told us a couple of weeks ago.
Yeah, there's no reason to panic.
There'll be reason to panic, but there is a reason to click. All right. Do we have any other questions for Andrew on the geology news?
Paul, is this Scott? I have a comment.
Please.
Can you hear me?
Yes.
Okay. Somebody asked the question about the Sea of Galilee and the old temple there that had the offset that is there. First of all, that was basalt. I have been to that area. That is a spreading center. And the eastern side of the Dead Sea and Sea of Galilee is moving in an easterly direction, and Israel is moving in a westerly direction. And so you have magma coming up and basalt in the middle in the past. So that was primarily basalt.
Interesting.
Awesome. Thank you, Scott. I did not know that.
And great job, Andrew.
Thank
I
you.
just love what you're doing. Keep it up.
Will do.
Well, we're a little before our 1:30 time. I'm going to turn off the record. I need to take a break. We have a couple people who have, I think Fred and who's the Jeff Lee. If you can stay on, we have some show and tell, some rock show and tell, and I mean stay and chat. If you have a rock now that you want to just show on your screen, if you don't have a photo of it to share, that's fine as well. We can go as long as 2 o'clock. And I know we had some other questions too. I'm going to turn off the record. I'm going to take a break personally. I'm going to get my map so we can do an unboxing and I can unroll it. And maybe some people can give me some advice about how to laminate a map like that so I don't just destroy it immediately.